My name is Adrian Macias. I'm going to present the result of our work entitled Exploring Player Experience of an Augmented Puzzle and Wearable for Studying Interaction between Parents and Children with Down Syndrome. This is the content of my presentation, which I will use to describe the PuzzleAction design and evaluation process. Directive behaviors are defined as any systematic use of command, request, and other controlling behaviors aimed at inducing a child to adopt a behavior desired by the parents. In this work, our interest is centered at the identification of action related to directive behaviors and the study of interaction between children with Down syndrome and their parents. What are the impacts of these behaviors? Down syndrome represents the first cause of intellectual disability worldwide, with an approximate prevalence of 1 in 1,000 live births. Mothers of children with Down syndrome tend to use directive behavior more often than mothers of typically developing children. When used in excess, children's autonomy and independence could be compromised. When using conventional methods, research on directive behavior is developed in the lab or naturalistic environments. For activities, particular objects selected by the researchers like puzzles and free play, where the child selects her preferred toys, are used. For data collection purposes, three methods are commonly used: direct observation, video annotation by trained observers, and paper-based instruments. Accordingly to literature, monitoring directive behaviors using technology in parent-child interactions have been little explored. Augmented objects or smart toys enabled by pervasive technologies are often used to develop rich technological environments with diverse purposes. Several works have explored the use of augmented objects or smart toys to monitor children's developmental progress and detect children's developmental delays. An example is Child's Play, a system for automatically characterizing certain types of object play behaviors performed by young children, since a specific play behavior might serve as an early indicator of autism. Other researchers have focused on investigating how augmented objects or smart toys can support different therapies. Access Block is a good example. It is a system that supports block therapy for preschool children with post-trauma stress. The system's goal is to automatically characterize play action for assessing a specific behavior in children's play using a smartwatch embedded toys block. Radio frequency identification technology is used in several works. However, little has been said regarding using augmented garments such as smart toys and wearables for studying interaction between parents and children with Down syndrome. The literature shows that studies on children with Down syndrome using sensor-equipped gloves are scarce, and none evaluates game experience. Still, it is unclear whether the use of augmented garments by children with Down syndrome will be challenging. We present the design and evaluation of PuzzleAction. An augmented object consisted of an augmented puzzle and an augmented garment, as embroidered gloves, intended to be used to collect data related to parent-child interactions. Next, I will present you the PuzzleAction design process. The PuzzleAction design process is composed by 3 steps. First, in the identification of relevant actions, we analyze 12 video recordings from a previous study, where parent-child dyads played with 3 jigsaw puzzles of distinct complexity. We aimed to identify actions that occurred during the interaction and that could represent a directive or intrusive behavior. We went further and broke down each action into a series of operations, realizing that some of the operation takes part in one or more actions. So we define a set of unique operations that, depending on a specific combination and arrangement, could be used to describe any of the actions. In the second step, requirement definition, using the observer actions and operation, we derive a set of requirements for designing augmented objects and garments for studying directive behaviors. The requirements reflect what the system would be capable of doing to detect the action related to directive behaviors. In step 3, using the derived requirement, we designed PuzzleAction. In this table, we show the results of the identification of relevant actions. In first column appears the behavior type. In the second, a brief explanation of the behavior type. In the third column, the action identified. And in the last column, the set of operations that describe the action. We identified 5 actions and 5 operations in total that potentially could appear as different actions. For example, Operation Z, a puzzle piece is taken by the parent child from the board, is part of action 2, 4, and 5. In the requirement definition, we define the requirement, which appears at the first column, the justification, which appears in the second column, and in the third column we show the solution proposal to fulfill the requirement. We define 9 requirements in total, 3 related to system attributes as puzzle action appearance and record of initial and final time, and 6 related to operations. This table represents the set of directive behavior currently supported by the design of PuzzleAction, the underlying actions used for inferring them, and the requirements met with each action. The augmented puzzle has 2 components, a physical puzzle and a virtual puzzle. At the start of the game, the virtual puzzle is displayed in gray color. We use the virtual puzzle to help the participants be aware of the capabilities of the augmented puzzle. Each time a child takes a piece, PuzzleAction emits an audible sound. For example, the sound of a siren if the figure has the shape of an ambulance. And when the child places a piece in the correct space on the board, an alert sound is played and the corresponding piece in the projector screen is colored. PuzzleAction also uses embroidered gloves to facilitate the communication between the physical and the virtual puzzles, as well as for monitoring the relevant actions that are critical for studying directive behavior. We decide to use gloves for tracking hands action because they can be augmented with different onboard sensors capable of collecting data to identify relevant actions, thus avoiding potential problems when using other types of sensors. For example, visual obstructions and going out from the detection field in optical sensors. In this image, you can see the deploying of PuzzleAction in a playing scenario. The physical puzzle is located on the table between the parent and the child, while the virtual version can be seen on the projection screen in front of the child. The projector is located next to the physical puzzle, and a pair of speakers is located on the floor between the projection screen and the table. The child and his parent are wearing the sensor-equipped embroidered gloves during all the game. The evaluation's overall goal was to investigate the game experience of children with Down syndrome while playing with PuzzleAction accompanied by one of their parents, and evaluate the experience of wearing gloves with visible electronic devices, for example, wires. The participants in the study were 12 children with Down syndrome, 4 female, ranging from 4 to 15 years old. Media equals to 11.8, and a standard deviation equals to 3.04. Also participated parents of children with Down syndrome, 8 female, and 2 therapists who participated as passive observers. 4 instruments were used during the study. PuzzleAction prototype based on the Wizard of technique. Even you can see the human wizard located behind the child. We also used demographic information questionnaire. This was used to gather information about the use of wearables of any type by the children. The game experience questionnaire, we used the core module of the JEC to measure the game experience of participants. Also, we added 2 items regarding the experience of using the embroidered gloves. Finally, we used the semi-structured interview that was applied to the therapist to investigate their perception on pros and cons, troubles or difficulties observed during the session, and for any relevant aspects for improvement of PuzzleAction. The procedure was divided in 4 stages. Stage 1 through 3 was applied to each parent-child diad, and stage 4 was applied to the therapist at the end of the each day. In stage 1, the parent answered the demographic questionnaire, and both the parent and the therapist signed an informed consent. In stage 2, the research group instructed the parent on the dynamic of the game and the need for his child and himself to wear gloves throughout the game. Then the parent and child played PuzzleAction, and once the game was over, the parent and therapist responded to the JEC as proxies of the child. In the third stage, the research group thanked the participants. In the final stage, a small structured interview was applied to the therapist. For data collection, we used non-participant observation during the sessions. 2 members of the research team, 1 therapist, and the participant were involved. The therapists participated as passive observers. The sessions were carried out at the Down Center facilities as per request of the institute we are collaborating with. Total effective game play time collected includes average playing time by parent-child diad was 3 minutes and 53 seconds, with a standard deviation of 1 minute and 41 seconds, a minimum playing time of 1 minute and 47 seconds, and a maximum of 7 minutes and 15 seconds. Aggregated time for all the ads was 46 minutes and 31 seconds. For data analysis, we use descriptive statistics to analyze participants' score for the JEC from both point of view, parents and therapists. An independent test was used to investigate differences between the perception score of the JEC dimension by parents and therapists. Each therapist answered only the JEC of the session where they were present. All answers were considered in the same set. To analyze qualitative data, we use content analysis using technique to derive grounded theory as open and actual coding. Quotes obtained from the open-ended question and interviews were grouped to uncover emerging themes related to the player experience of participants playing with PuzzleAction. Related to results, from the point of view of both parent and therapist, the children had a positive player experience at the dimension of competence, immersion, and positive affect, had an average score above the mean score, 2.0. They didn't feel frustrated because tension and negative effect were under 1.0 both. Also, they felt relaxed, tension was less than 0.2, and with a positive attitude, positive effect was greater or equal to 3.15. They felt imaginative and intensely concentrating the game. Immersion was 3.29, but without reaching a state of flow. Flow was under 2.0. An explanation for this could be related to the short duration of the experiment's task, together with the low complexity of the game. Challenge was 0.92 for parents and 1.63 for therapists. T-tests showed no significant differences in any of the dimensions related to children's player experience. And regarding the dimension of glove comfort, parents rated higher than therapists, means equal to 3.25 against 2.83. However, the mean difference was not significant. On physical design, most of the children had problems with putting on the gloves, resulting in a request for help from their parents to wear the glove correctly. Once the children had the gloves on, they continued playing with no complaints. Both parents and therapists agreed that the design of the gloves should be adapted to the characteristics of children with Down syndrome. The more relevant theme around PuzzleAction was that the physical puzzle should have different levels of complexity. In this way, children can master their solving skills at different levels without losing interest in the short term. Conclusion and future work. Our design addresses the automatic analysis of what happens in structured activities where two people participate. Unlike other augmented toys or objects, this puzzle works in conjunction with the gloves and have a mechanism to identify the type of actions that occur during parent-child interactions, particularly related to directive behaviors. The evaluation results showed that PuzzleAction provided a positive player experience to children with Down syndrome. For future work, we plan to implement PuzzleAction and evaluate its ability for automatic monitoring of parent-child interactions. Finally, we would like to thank the therapist and director of Centro Down for their continuous support. We also express our gratitude to the children and their parents for the enthusiasm during the development of the study. Thank you.